The ice protection system includes the following subsystems: the slat anti-ice system and engine anti-ice system. For these systems, the bleed system provides the thermal energy. The pitot and static port heating system, windshield anti-ice system, and water lines heating systems use electrical power to prevent icing. The ice detection system activates the automatic operation of the slat and engine anti-ice systems. The slat anti-ice system provides wing anti-ice flow and temperature control to meet all aircraft operating requirements. The system controls the flow of hot bleed air from the engines to the left and right wing slat piccolo tubes. The left and right systems are identical. Skin temperature sensors and a pressure sensor provide signals to the air management system controller for system monitoring and to modulate the slat anti-ice valves. The system interfaces directly with the ice detection system to provide fully automatic system activation when an icing condition is detected. The nacelle anti-ice NAI system supplies hot air from the engine to the inlet cowl to prevent hazardous formation of ice on the inlet lip. System control and monitoring are provided by the AMS controller based on signals from the pressure transducer and pressure switch. In response, the AMS controller will modulate the NAI pressure regulating shutoff valve. The system primary automatic operation is activated by the ice detection system. The NAI system for each engine is completely independent of the other engine. NAI bleed cannot be shared between engines. Each of the smart probes and total air temperature probes include resistive elements to ensure de-icing and anti-icing sensor accuracy in an icing environment. Power is distributed to the probes when the aircraft is in the air or when at least one engine is running. Windshield ice and rain protection consists of two subsystems: the windshield heating system and the windshield wiper system. The windshield heating system regulates the windshield temperature in order to prevent ice formation on the exterior of the windshield and fog formation on the interior surface. System control is provided by the ice protection control panel, windshield switches 1 and 2. The water system ice protection includes forward and aft drain mast heating to prevent hazardous ice formation during draining of water. Water fill drain nipple heating is provided to prevent clogging of the fill and drain lines, which could cause freezing of residual water. The system on-off selection is controlled by the water waste system controller, depending on the outside air temperature. The water distribution lines are routed through the pressurized cabin, where temperature is maintained above freezing. System components are also designed to withstand repeated freezing and warming cycles without damage. The ice detection system provides fully automatic airfoil and engine anti-ice system primary activation. The system includes 2 ice detectors, which are mounted forward and below the windshield. The main purpose of the detectors is to detect icing condition before the critical surfaces are affected. The Ice Protection System Flight Deck interface is provided via the Ice Protection Control Panel. Control switches for engine and airfoil anti-ice permit selection of engine anti-ice 1 and 2 and wing anti-ice on or off. When the switch is selected off, the strip bar is shown in the switch, and when selected on, the switch is dark, according to the dark cockpit philosophy. When actual anti-ice is operational, an ICAS message is provided for the respective system. Engine or wing anti-ice operation also depends on the position of the mode switch. In auto position, engine and wing anti-ice will be activated by an ice detector signal. In override position, engine and wing anti-ice will be activated by a weight-off wheel signal. The test selector switch has 3 positions: engine, off, wing. During ground test, the switch will activate the respective system if engine and wing anti-ice is selected to auto. A flight deck interface for selecting windshield anti-ice is also provided on the ice protection panel. Switch selection for these systems will connect electrical power to windshield 1 and 2. Windshield heating will be operational when the engine is running or the aircraft is weight-off wheels. The Ice and Rain Protection System's status indication has 3 parts: the Central Maintenance Computer (CMC) messages, selectable from the MFD System menu, to provide fault codes, fault storage, and a review function to assist in troubleshooting. The Engine Indication and Crew Alerting System, advisory, caution, or warning indications, and the Anti-Ice Synoptic page selectable from the MFD System menu, which indicates system temperatures, pressures, and valve positions. The slat anti-ice system utilizes hot bleed air from the engine to supply thermal energy through the slat anti-ice valve via the telescoping duct to the slat 2, 3, and 4 piccolo tubes. Holes in the piccolo tubes cause the hot air to impinge on the inner surface of the slat, creating the heat needed to prevent ice on that slat. The AMS controller receives signals from the pressure transducers and from the slat skin temperature sensors to modulate the slat anti-ice valve. System automatic operation is activated by the ice detection system. However, in flight, the pilot can override the ice detection system and actuate the slat anti-ice manually. The selector switch is provided on the cockpit control panel for ground tests. The slat anti-ice valve located in the pylons is a butterfly valve powered by a pneumatic servo actuator. The valve modulates to maintain the required flow to the slats for anti-ice, controlled by the AMS controller. Duct pressure is ported directly to the supply of the actuator piston. This pressure force and the spring force provide the closing force for the butterfly disc. The opening force is provided by servo pressure acting on the larger servo piston. The servo pressure is controlled by a torque motor mounted on the valve, which receives an electrical signal from the AMS controller. The anti-ice flow is based on altitude, ambient temperature, Mach number, and slat position. The microswitch installed on the valve indicates a closed position or valve modulation. The signal is also used for built-in test purposes. The slat anti-ice temperature sensor is a dual-element platinum resistance sensor which monitors the slat skin temperature. 3 sensors are mounted on each wing outboard of slat 2 and inboard and outboard of slat 4. During normal operation, the middle sensor on slat 4 is used for the calculation of proper ice flow. The remaining 2 sensors are used for health monitoring to ensure that hot air covers the entire area where ice protection is required. The slat anti-ice pressure sensor is used to monitor duct pressure downstream of the slat anti-ice valve on each wing. The sensor sends an electrical signal to the AMS controller, which is used for system control and health monitoring. The sensor is hermetically sealed and consists of a pressure port, pressure transducer, and electrical connector. The sensor receives 28-volt DC excitation voltage. The slat anti-ice system contains a telescoping duct on each wing to connect the piccolo tube with the anti-ice pressure supply duct. The telescoping section of the duct is Teflon-coated stainless steel, which rides on two bearings. The telescoping duct extends and retracts with the wing slat and allows uninterrupted flow during wing slat actuation. The slat anti-ice system contains steel piccolo tubes that run through the wing slat. Regulated bleed air flows through the telescoping duct and pressurizes the piccolo tube. The piccolo tube contains holes that allow hot air to flow out into the wing slat chamber for heating the slat skin. The piccolo tube consists of 3 separate duct sections. When assembled into the aircraft, these duct sections are connected in between slats by flexible sleeves to allow movement. The slat anti-ice protection system can be operated in 2 different modes, auto or override. Selectable on the overhead control panel. In auto mode, the ice detection system will actuate the system operation, while override can be selected manually in the air. In both cases, the slat pressure regulating shutoff valves are modulated by the AMS controller. The desired skin temperature is calculated as a function of slat position, ambient temperature, Mach, and altitude in the range of 71 degrees Celsius, 160 Fahrenheit, to 121 degrees Celsius, 250 Fahrenheit. The AMS controller calculates the desired skin temperature to determine a duct reference pressure. The controller then compares the calculated and actual duct pressures measured by the pressure sensors. The AMS then modulates the pressure regulating valves by increasing or reducing the torque motor current. If a fault is detected that disables anti-ice flow on one wing, the system will automatically command the opposite wing's anti-ice valve closed. The following slat anti-ice system status, advisory, or caution messages can be indicated on the ICUS. Status message, anti-ice wing valve open from the valve position switch. Advisory message, anti-ice mode not auto if the mode selector is not in auto mode. Advisory message, ice condition when ice is detected in flight. Caution message, anti-ice, low capacity, if air is commanded on and the system is not failed, but the pressure or temperature is low for slat anti-ice. Warning message, anti-ice wing leak, if the detection loop signals that internal temperature of the slat exceeds 130 degrees Celsius, 266 Fahrenheit, for 30 seconds. Or, internal temperature exceeds 150 degrees Celsius, 302 Fahrenheit, for 2 seconds. Caution message, anti-ice wing fail when valve fails, or due to asymmetric operation, over temperature, over pressure, or piccolo burst. A caution message, anti-ice wing no dispatch, is displayed whenever a wing anti-ice bleed valve has failed open. The slat anti-ice system contains test logic that monitors the performance of the system components. Any component or sensor failure will be indicated through the aircraft diagnostic and maintenance system, or via the ICUS. The anti-ice synoptic page also indicates the system temperature, pressure, and valve positions. In addition to the built-in test, it is possible to test the system by using the control panel test switch. When bleed source is available, the engine or APU and the wing anti-ice switch are on, then selecting the test switch to the wing position will activate the slat anti-ice system. When the engine is running, the engine's anti-ice system extracts air from the engine fifth-stage compressor. The air that flows into the engine anti-ice system, EAIS, is controlled by the engine anti-ice system valve. The valve is fail-safe open, assuring that the valve will default to the open position in the absence of an electrical signal. Through the inlet forward bulkhead connection, the air passes into the swirl nozzle and exits through jets in the tube wall. The air collected in the D-duct then exits near the bottom of the inlet into the atmosphere. The system is monitored and modulated by the AMS controller, either automatically activated by the ice detection system or by the pilot override command. The AMS receives signals from the pressure transducer to monitor system operation. The engine anti-ice system valve is located in the system supply ducting in the fan compartment. The engine anti-ice valve is an on-off, shut-off valve and is electrically controlled, pneumatically operated to the loaded open position. The valve contains an integral position switch to indicate when the valve is in the open position. The flow-limiting venturi is located in the core compartment downstream of the NAI valve. The primary function of the venturi is to protect the inlet structure, in the event of a piccolo pipe failure, by limiting the mass airflow rate entering the forward D chamber of the inlet. In case of a duct failure in the upstream duct, the restricting effect of the 1-inch diameter duct alone limits the bleed flow to acceptable amounts. The engine anti-ice pressure transducer is located in the fan compartment in the anti-ice air supply duct. The pressure transducer monitors the engine anti-ice system pressure and sends a signal to the aircraft systems to indicate if the engine anti-ice system is pressurized. If a failure occurs inside the shrouded anti-ice duct, either in the fan or in the inlet section, the pressure transducer will transmit a failure signal to the aircraft maintenance recording systems. The forward bulkhead and the inlet lip form a D-duct. The forward bulkhead has an opening with a mounting bracket for the anti-ice system. The mounting bracket couples the anti-ice duct to the swirl nozzle, which distributes the anti-ice air over the inner surface of the inlet lip. The anti-ice air exits near the bottom of the inlet into the atmosphere. The T2 sensor mounted in the inlet cowl transmits a temperature signal to the FADEC. The sensor is electrically heated to prevent ice formation. The engine anti-ice protection system can be operated in two different modes, auto or override, selectable on the overhead control panel. In auto mode, the ice detection system will actuate the system operation, while override mode can be selected manually in the air. The ice detector and cockpit switches provide signals to the modular avionic units 1 and 2, and also a mode signal to SPDA-1. MAU-2 and MAU-3 also communicate with the FADECs, which provide engine parameters and inlet temperature signals. Pressure transducer and pressure switch signals are sent to MAU-1 and MAU-3 for monitoring and leak detection. Finally, depending on system internal logic, SPDA-1 and SPDA-2 provide signals to modulate the left and right engine nacelle anti-ice valves. All MAUs 1, 2, and 3 and SPDAs 1 and 2 are connected via the Aviation Standard Communication Bus to provide information, indication, and failure signals to the CMC and ICAS. The following engine anti-ice system status, advisory, or caution messages can be indicated on the ICAS. The status message, AI, engine 1-2 valve open, indicates that the NAI valve is open. The advisory message, AI, engine 1-2 fault, is displayed during test if there is a loss of capacity to monitor the adequate functioning of the system. The advisory message AI engine 1-2 leak is displayed if the system detects a leakage in internal pipes. The caution message AI engine 1-2 fail indicates that the NAI valve is closed after an open command or that an NAI duct failure is detected. The engine anti-ice system contains test logic that monitors the performance of the system components. Any component or sensor failure will be indicated through the Aircraft Diagnostic and Maintenance System, or via the ICUS. The anti-ice synoptic page also provides indication for nacelle anti-ice valve positions, in addition to the built-in test. The system can be tested by using the control panel test switch. When the engine is running and engine anti-ice is on, moving the test switch to the engine position will activate the engine anti-ice system. The pidostatic sensor heating system provides electrical power to heat the air data smart probes 1, 2, 3, and 4, and the total air temperature 1 and 2 probes to maintain their accuracy. Self-resistive elements are installed in each ADSP and total air temperature probe. Heating is controlled by the air data computers, which are part of the air data smart probes. Additionally, ADC1 controls the heating of total air temperature 1, and ADC4 controls the heating of total air temperature 2. The ADC monitors the probe current to detect any failures and actively controls the heater temperature. Each smart probe consists of a multifunction probe and an air data computer in one assembly. The multifunction probe includes a single self-resistance element in the strut and in the probe head. The air data computers perform probe heat controlling and monitoring functions. The actual power sources for the different probes are DC bus 1 for probe ADSP1 and ADSP2 via the left integrated control center, DC bus 2 for ADSP4 via the right integrated control center, and DC essential bus 3 for ADSP3. The total air temperature 1 probe is part of the Air Data System 1. Heat control and monitoring for this probe are provided by Air Data Computer 1, which is part of ADSP1. The actual power source for the heating element is DC bus 1 via the secondary power distribution assembly. The TAT2 probe is part of the Air Data System 2. Heat control and monitoring for this probe are provided by Air Data Computer 4, which is part of ADSP4. The power source for the heating element is DC bus 2 via the SPDA. The Air Data Computer controlling logic measures the voltage supplied to the heaters and the current to each heater. The logic then adjusts the duty cycle in increments of 10%, from 10% to 100%, to supply more or less average power depending on the current level. If an abnormal condition is identified, such as a current monitor failure or a voltage monitor out of tolerance or under voltage, the heater control function will force the heater to operate on 100% duty cycle or full power. In auto mode, the aircraft systems will apply power to the multifunction probe and total air temperature heater if the aircraft is airborne or any engine is running. Smart probes and total air temperature probes are tested by the built-in continuous test during every software cycle. The test will check heating and sensing elements for open or shorted circuits. The smart probe and total air temperature probe heating-related failure messages are displayed on the ICUS and on the CMC. Refer to ATA Chapter 34 for further details regarding the failure messages. The windshield is electrically heated and constructed of laminated glass. The outboard ply is coated with an anti-static film to provide a discharge mechanism for static buildup, which helps to prevent damage to the heating system. The windshield heater is a film located on the inboard surface of the outer glass ply, which provides anti-ice capability. There are 3 sensing elements, 2 connected to the windshield heater control unit, WHCU, and 1 that is considered auxiliary. Electrical connections are provided by a terminal block with 8 lugs, 2 connected to the power supply units, and the other 6 for the 3 temperature sensors. The windshield wiper system consists of 2 mechanically and electrically independent subsystems, 1 for each windshield. The subsystems include windshield wiper motor converter, wiper arm, wiper blade, and control switch. The motor converter assembly decodes signals from the wiper control switch and provides power and speed control to the motor. The windshield wiper system is operated from 2 wiper control switches located in the cockpit. All maintenance of the converters, arms, and blades can be accomplished from the exterior of the airplane. The motor converter, located in the nose section in front of the windshields, converts the rotary input from the motor into oscillating motion needed to sweep the blades across the windshield. The windshield wiper motor converter unit converts high-speed rotary motion of its electric motor to usable low-speed and high-torque oscillatory motion of the output shaft. Power input to the controller is 28-volt DC from bus 2 and bus 3, while rectification input to the motor is 115-volt AC. When both pilot and co-pilot wiper control switches are set to the same position, the pilot motor control assembly acts as a master and will synchronize the blade sweep. The windshield wiper system is operated from the cockpit control panel. The panel includes 2 selector switches, and each of the switches has 4 different positions. In off position, the associated wiper blade travels to the windshield inboard position, parking out of the pilot vision. When the selector switch is in low position, the wiper operates at 80 cycles per minute. When in high mode, the wiper operates at 125 cycles per minute. Timer mode provides an intermittent high-speed operation of the associated windshield wiper in single cycles, 2 strokes, with a 7-second time interval between the cycles. Operation of the wipers can be independent in low, high speed, and timer mode, or synchronized when both selector switches are selected to the same position. Synchronization occurs within 8 strokes for low and high speeds, and after 1 stroke for timer mode. When the switch is selected off, the controller reverses the motor and moves the blade to the off-screen parked position. In the stationary condition, the controller will employ an electromechanical brake for position holding. Dry windshield operation leads the motor converter to a stalled condition due to high friction. The controller senses the motor converter current surge and drives the arm directly to the parked position. The system remains inoperative until the selector is set to off and a new operation mode is selected. The windshield heating system consists of left and right windshields, left and right control units, left and right switches on the ice protection control panel, and components of the left integrated control center, right integrated control center, and SPDA1. Each windshield heater control unit independently regulates the temperature of a windshield using two sensors and one heater element that are integrated into the windshield. One sensor is used for control and the second is an overheat monitor. In addition to regulating windshield temperature, each windshield heater control unit monitors system integrity using continuous and power-up built-in test. The windshield heating control units located in the front electronic compartment have discrete lines to SPDA1 to facilitate initiated built-in test, fault reset commands, and enable fault code information to be sent to SPDA1 and via ASCB to the CMC and ICUS. The windshield heater control unit also has an output to control a contactor located in either the LICC or RICC. The windshield heater control unit and contactor use 28-volt DC power controlled by the windshield heating switch. Heater power is 200-volt AC, routed via the contactor to the windshield heater control unit, which in turn switches power to the heater. The windshield heating operation starts when the windshield button is pressed on the ice protection panel. The windshield heater control unit drives the contactor coil to close and verifies the output capability and the integrity of the contactor and heater. The ramp warm-up function automatically modulates heat command by a duty cycle that increases in steps from 0 to 100%. Over a period of 3 to 4 minutes. During normal control mode, the windshield heater control unit switches heater power on when the control sensor temperature is below 34 degrees Celsius, 93 Fahrenheit, and switches the heater power off when the temperature is above 37 degrees Celsius, 98 Fahrenheit. The controller also monitors for an overheat condition, which is signaled at 52 degrees Celsius, 125 Fahrenheit. The windshield heating system will provide CMC or ICUS indication if a sensor fails, a contactor fails, in case of a short circuit, or if the system detects an overheat condition. The respective system ICUS caution messages, Windshield Heater Control Unit 1, or Windshield Heater Control Unit 2 will appear on the display. In case of windshield wiper system failure, the associated message will be shown on the CMC. The waterline's ice protection system includes fill-drain nipple heating and forward and rear drain mast heating. Fill-drain nipple heating power is 115-volt AC and is applied via the left integrated control cabinet contactor from the AC service bus. Actual heating is selected on and off depending on the temperature at the control thermostat. The heating element is a cuff installed around the fill-drain nipple. Drain mast heating power of 115-volt AC is supplied by the AC ground service bus through the Water Waste System Controller, WWSC, and the SPDA. The drain mask contains a safety thermostat and a temperature sensor for external temperature control. The WWSC temperature control circuit enables or disables the SPDA to provide power to the drain mast heater. The self-regulating cuff heater is an electrothermal device made of silicone elastomer and operates on 115-volt AC single phase at 40 watts. The thermostat within the heater maintains the temperature between 38 degrees Celsius, 100 Fahrenheit, and 49 degrees Celsius, 120 Fahrenheit. The fill-drain nipple cuff heater circuit is protected by a 3-phase 7.5 amp circuit breaker in the left integrated control center. The waterline's ice protection system drain mast heating consists of a heater with overheat protection, a safety thermostat, and a temperature sensor. The WWSC will enable or disable the SPDA to allow the heater to maintain a temperature of 71 degrees Celsius, 169 degrees Fahrenheit. In case of a heater failure and the drain mass temperature drops below 5 degrees Celsius, 41 degrees Fahrenheit, the safety thermostat will open, so draining of potable water is no longer possible. Drain mass heating power of 115 volts AC is supplied by the AC ground service bus. The controller is able to monitor system and component failures and addresses messages to the CMC or to the flight attendant panel. The flight attendant water system fault LED indicator is on if the indicated temperature of the forward drain mast is continuously less than 35 degrees Celsius for 5 minutes, or if the indicated temperature of either drain mast is continuously greater than 70 degrees Celsius for 2 minutes. CMC provides two kinds of messages: forward drain mast fault or aft drain mast fault. Both failures will inhibit the in-flight drain system. The ice detection system includes two ice detectors directly connected to the modular avionic units that send signals across the avionic standard communication bus to the air management controller located in the secondary power distribution assembly. The AMS has two channels to provide ice detection system monitoring and control. The ice detection system provides test capability by the overhead ice protection panel test switch and failure messages for CMC or ICUS display. The ice detector is a single component including a sensor and microcontroller in one unit. The sensor includes a driver which is vibrated at a 40,000 Hz frequency by the oscillator, and a feedback sensor to monitor this frequency. A heater element is also installed in the sensor section. The microcontroller interconnects with the aircraft harness. Input to the microcontroller includes 115-volt AC power, press to test, and reset. Outputs are ice signal and sensor fault. The ice detection system operates if, on the overhead ice protection panel, the mode switch is on auto. If ice builds up on the ice detectors, as sensed by the feedback sensor as a probe frequency change, then the microcontroller sends an ice signal to the modular avionics unit, which transmits an ice condition signal to the ICUS. At the same time, the airfoil and engine intake anti-ice cycle starts, and the ice detector probe will be heated for a few seconds to melt the ice from the probe. Anti-icing is continuously in operation as long as ice is detected on the ice detectors. If the mode switch is selected to override, the ice detection system is disabled, and airfoil and intake will be continuously anti-iced in flight. The system provides failure messages on the CMC and on the ICUS display. The ICUS advisory message, ice condition, indicates that the left or right ice detector has detected icing condition in flight. This message is inhibited below 1,700 feet above airfield. The ICUS caution message, ice detector 1-2 fail, indicates ice detector failure. If one ice detector fails, the aircraft can be dispatched into icing conditions. If the second ice detector also fails, the aircraft cannot be dispatched into known icing conditions.